we are now going to show that the construction of this collection of upper functions and the integral on them is actually a more general thing than the Riemann integral. We are going to do this by first of all showing that all Riemann integrable functions are automatically upper functions, combined with the observation that there is an example of an upper function such that the negative of that upper function is not an upper function, will clearly show that the collection of upper functions is actually a larger class. So we are going to show that Riemann integrable functions are upper functions. To do that, we need to recall the Riemann-Lebesgue theorem that we have seen already in real analysis 1. What does the Riemann-Lebesgue theorem say? It says that a bounded function f from AB to R is Riemann integrable if and only if the set of discontinuities is a set of measure 0. This is a necessary and sufficient condition for Riemann integrability. The theorem we are going to show now is the following. If f from AB to R is Riemann integrable, then f is an upper function and the Riemann integral of f coincides with the integral we have defined for upper functions. So this makes the collection of upper functions a proper superset of the collection of Riemann integrable functions. Proof. So let f be Riemann integrable. What we are going to do is we need to find a sequence of step functions that generate this function f. We know that the set of discontinuities of f is really a negligible set. We also know that the Riemann integrability of f will give that the upper sums and the lower sums of this sort of get closer and closer to each other. Since we want step functions less than or equal to f, we will mimic what we did for the evaluation of the lower sum. What we are going to do is we are going to consider partitions obtained by repeatedly dividing AB, repeatedly bisecting AB. In other words, Pn is a partition, or rather P2 power n, that's a better notation. P2 power n is a partition, or is the partition of AB consisting of points that are B minus A by 2 power n apart. Okay, so this partition will obviously have 2 power n points. Okay, so what we essentially do, for instance, if you take the case AB and you take the case n equal to 1, you just take B minus A by 2. This a plus b, or rather this will be a plus b minus a by 2. These 3 points would be the points in the partition. So to be precise, there will be 2 power n plus 1 points. Okay. Similarly, when you consider P2, which is P2 power 4, you will have 2 more points. You will have 2 more points for a total of 5 points. Now the key thing that is very, very interesting about this sequence of partitions is obviously P2 power n plus 1 is a subset of P2 power n. Okay, so these partitions are sort of nested, and this is going to be crucial. Now let's redraw this picture again to get better insight of what is about to happen. So let's just draw some. This is actually a plus b by 2. I can call it that. We have this. We have some function. And at some points it's not continuous. So let's say at here it's not continuous. We have this function. What we are going to do is we are going to sample the lower sums. That is, essentially look at the points of minima. For this first interval, it's somewhere like here. So this will be the first piece, and for the second piece also it's almost at the same place. So it will look like this all the way till here. Then for the third piece it's somewhere over here. It's sort of jumping. Okay, and this is the step function we are going to consider. So we have to extend this f all the way here, and then finally we have another piece which is like this. Okay, so what we are going to do is we are going to define mk by definition to be infimum of f of x as x runs through x k minus 1 comma xk. Okay, where we are denoting the various points of the partition. So the points of the partition, there are 2 power n of n plus 1 of them are denoted xk. Okay, so we just define small mk to be infimum of f of x as x runs through xk minus 1 xk, and we define Sn to be the step function that takes the value mk on the interval xk minus 1 xk. Fine. So we have essentially the picture I drew, that is going to be the step function Sn. Now clearly Sn plus 1 is greater than or equal to Sn. Why is that the case? Well, look at the various subintervals you get when you divide the partition Pn to the partition Pn plus 1. Sorry, P2 power n to P2 power n plus 1. You are halving each interval. Therefore, when you take the infimum on the smaller intervals, the infimum can only increase. So that shows that Sn plus 1 has to be greater than or equal to Sn. Okay, so Sn is an increasing sequence of step functions. Now what we are going to show is Sn increases to f almost everywhere, and the way we do it is to use continuity. So let x in AB be a point of continuity of f. Okay, fix epsilon greater than 0. We will show that for large n, Sn of x is less than or equal to f of x plus epsilon. Okay, and since epsilon was arbitrary, this will show that Sn's increase almost everywhere to f, because the set of points of discontinuities of f is a set of measure 0. Okay, now by continuity we can find delta greater than 0 such that f of y is less than f of x plus epsilon for all y in the interval x minus delta x plus delta. Okay, in particular if n is chosen so large that this entire interval xk plus 1, the length is less than delta by 3, that is the length of each subinterval, that is b minus a by 2 power n, is less than delta by 3, then xk plus 1 would be a subset of x minus delta x plus delta for some k. Okay, and x is in xk plus 1. So what is this trying to say? Well, if you choose the size of the partition to be so small, then what will happen is eventually the length of these intervals is so small that eventually this interval has to be a subset of x minus delta x plus delta, that particular one which contains x. Okay, now we want to do the correct estimate, so I have made a small error. Let me fix that such that f of y is greater than f of x minus epsilon. You will understand in a moment why I need this inequality, that is also a consequence of continuity, rather than the one I wrote down originally. Okay, so we know that Sn is going to take the value little mk on xk plus 1. But by the way we have set up things, xk plus 1 is a subset of x minus delta x plus delta. Okay, which means this mk will have to be greater than f of x minus epsilon. Okay, so in other words, f of x is less than mk plus epsilon, and we obviously have that mk is less than or equal to f of x, simply because mk was obtained by taking the infimum on this interval xk plus 1, and x is an element of this. Okay, now this clearly shows that mk's increase to f of x, or rather to be 100% precise, we have to write Sn of x is equal to mk is less than or equal to f of x equal less than f of mk plus epsilon equal to Sn x plus epsilon. Okay, so this clearly shows that Sn of x increases to f of x. Okay. Since the set of this argument holds, for any x at which f is continuous. So Sn increases to f almost everywhere, as claimed. Okay, so we still have to show that integral over I Sn is bounded above. This sequence is bounded above. Well, that's obvious because integral over I Sn is going to be less than m times b minus a, where m is equal to supremum of fx as x ranges through closed interval ab. Recall that f is a bounded function being Riemann integrable. Therefore, there will be a supremum for this function on the whole interval closed interval ab. Now, what does this allow us to show? Well, this shows that f is an upper function and the integral over I of f is nothing but limit n going to infinity integral over I of Sn. But this limit n going to infinity of integral over I Sn is nothing but the lower sum of f with respect to p2 power n. Right? And an exercise in real analysis 1, if you have not solved that exercise, solve it now. An exercise in Riemann integration theory will tell you that LFP2 power n actually converges to integral a to bf. Okay, since the mesh of the partition is becoming smaller and smaller, this will actually show that this will have to converge to integral a to bf. Hence integral of if is equal to integral a to bf as claimed. So both notions of integral, both the Riemann integral as well as the upper integral that we have defined, thankfully coincide for Riemann integrable functions. As I remarked earlier, there are functions, you should definitely solve the exercise in Apostle, where you construct a function f whose negative is not an upper is not an upper function. That is, an upper function whose negative is not an upper function. This will show that the set of upper functions is a proper superset of the set of Riemann integrable functions. In the next set of videos, we will define and study the basic properties of the Lebesgue integrable functions. Lebesgue integrable functions are those which do not have this annoying property that the negative is not integrable. We will get rid of this unnatural and not nice thing in the next video. This is a course on real analysis, and you have just watched the video on Riemann integrable functions are upper functions.